look good, but actually surprisingly, linear interpolation looked okay once you started staggering when that interpolation starts, because when you've got like just a mass of stuff that you're seeing, then it all sort of smooths itself out in a weird way. And then I tried techniques like taking the current position, the previous position, and the one previous to that, and like making a little Bezier curve out of it, and tweaking the weights and so on, and just tried a bunch of different things, and nothing really looked super convincing. But if you've been paying attention to the talk so far, then you might have already figured out what solution I used. There's a little clue earlier. Any guesses? Close, yeah. So basically, I used the same steering algorithm that we used for the fish system. So with steering, we treat the latest position, or rather not the latest position, but the sort of the one that we receive after the latest position. So we've got the current position that we receive, we've got the one previous to that, and we actually interpolate, or rather steer, towards that previous position. The reason we do that rather than steering towards the latest position is to account for network latency, so that if our packets aren't coming in on time, then we don't get a lot of sort of starting and stopping. This does introduce some inherent delay into the system. There's a few seconds of delay sometimes where a player will move, and it might be 2 or 3 seconds until you see them actually move on the other end. But for the type of experience that we were trying to create for the concert, this seemed acceptable. And then in addition to just this basic steering idea, I also added in extrapolation so that it would account for that network delay for specific types of movement that we were doing in the concert. But the basic idea is the same as what we used for the fish system. And you might also have realized that this won't give us an exact one-to-one reconstruction of the player's path, because you lose a lot of that high-frequency data. But on the whole, it looks really smooth and natural. So the second question now, can we reduce the number of bytes used by a position? Can we do this? Can we use a 16-bit floating point representation to cut our position size from 12 bytes to 6 bytes? So quick refresher on 16-bit floats, often referred to as half. We get 1 sign bit, 5 exponent bits, and 10 fraction bits. So it means that we get good precision when the values are small, but it gets exponentially worse as the values increase. So half floats are often used in shaders where precision is less important than saving memory bandwidth. And here's a few examples of what those precision limitations look like. So for those small values less than 1, we get a lot of precision, but it gets rapidly worse as we go into higher values. So if our value is 1024 or above, then the minimum interval that we can represent at that point is 1. So we actually just can't even represent fractional values at that point. So half floats are a really nice way to compress data compared to normal floats when the values are small, but they're really not a good fit for things like world positions, which can have large ranges and need consistent precision along that range. I mean, think about it. We only have 2 bytes, so only 65,536 possible values per component, which really isn't enough for representing world positions, especially in the large levels that we were going to be using for the concert. So does this mean that we're out of luck? Well, what if instead of storing absolute positions, we just store a vector pointing from our position to the position of the other player? So now we have small XYZ values for players that are close to us, and then at that point we get a lot of precision, and large XYZ values for players that are far away from us, where we get much lower precision. But this is actually great, because in a 3D game, objects that are far away inherently don't need as much precision in screen space due to perspective projection. So when it's far away, it's smaller on the screen, and each pixel represents a larger interval in world space. So those large intervals that we get between values as they start to increase don't really matter so much. So here's a test showing the difference between the 32-bit and 16-bit positions. So the size of the green dot here indicates the proximity to the player. And these are our original uncompressed positions. And watch closely. These are our viewer-dependent compressed 16-bit positions. So did you notice the difference? Probably not much of one, right? It's basically imperceptible. So it's completely worth the savings that we get from cutting our positional data in half. OK, back to our list of questions. Well, it turns out that we actually didn't even need to address these last three, because solving the first two was good enough. We now have a 2 times reduction in data rate from the positional compression and a 10x reduction from reducing the data frequency. And in the end, in fact, we used an update rate of 1 update every 1.5 seconds instead of every 1 second, because visually, I actually don't notice that much difference. So we ended up with a 30x reduction in our data rate from our original calculation, from 9 megabits per second all the way to 0.3 megabits per second. And that's equivalent to the bandwidth that you would need to play back like a potato quality video. So we felt comfortable that we would be able to handle that. Now, there was still a problem with the compression approach for the positions that I hadn't thought about when I was working on this. And some of you might have already guessed what it is, and if you have guessed what it is, then please talk to one of our fine people over here after the talk, because we'd love to talk to you. But anyway, I'll get back to that. So it was around August of 2022. We had around 3 months left to deliver the build that would be used for the concert in December. So we'd gotten the networking and rendering figured out, representing players as creatures, but we really hadn't been focusing too much on the Coliseum itself, which is where you'd start and end the concert. So our original idea was to have players represented as fixed points of light, perhaps with a way to turn their light on and off or change its color. But this just seemed a little bit underwhelming compared to the creatures that we'd be transformed into during the songs. But our team had another insight. If we're able to render creatures through the instancing system, then why don't we try to design an abstracted version of our sky characters? So one that doesn't require intricate bone-based animation and can be animated procedurally in the same way that we're animating all of the other creatures. So it wouldn't have to look exactly like the player's avatar. It would just have